Welcome back to Elements of Chemistry. Today we're going to continue on our nuclear discussion, talk about nuclear equations. So in our previous video, we covered 6 of the main types of nuclear equation or particles, energy, that you're going to get in a nuclear equation, the ones you're going to see in an average high school class. So the first thing we're going to talk about is an alpha decay. In an alpha decay, we have a large, heavy nuclei. They're generally going to undergo an alpha decay because they need to lose mass to approach that band of stability. Remember, they want the neutron-proton ratio to be 1. Yes, we are giving human qualities to the atom. I know they don't really want anything. It's just a good way to think about it. Okay, so the key is that top number n on each side of the equation has to balance. The top number, and it's shown here in blue on this one, is the mass number. So we've got uranium with a mass of 238. It's going to decay by an alpha emission, that 4/2He. And you think of the arrow like a big equal sign. The numbers on the top have to add up on either side. That's the mass. Same thing with the bottom numbers. That's the atomic number. They have to add up on either side of the equation. So if we had a different one like 234 uranium, it's got a different mass. If it underwent an alpha decay, and notice I'm not putting a fraction bar in here, it's just mass over atomic number. We can predict what this daughter, remember parents decay into daughters, the helium or alpha particle, this is my alpha, is an ejected particle. Well, the top numbers have to add up on either side, so that's going to be 230, because 230 plus 4 is 234. What do I add to 2 to get 92? Well, that's going to be 90. And then I just need to look for a periodic table and figure out what element 90 is. If we look at our periodic table, and I happen to have one right here, element number 90 is thorium, so we're going to put the symbol TH. You got to have a periodic table when you go to do these problems. So there's an alpha. A beta decay occurs when the nuclei needs to lose a neutron to approach the band of stability. This is going to increase its number of protons. So my atomic number is going to go up. But once again, the numbers on top add up on either side of the equation. And the numbers on the bottom have to add up on either side of the equation. And that 0 over negative 1e, that is my beta particle. You can show it multiple ways. So let's do another one. If we had, let's just pick one for fun. Let's do cesium. Cesium's atomic number 55. And let's say we have cesium 132. If that underwent a beta decay, 0 over negative 1e, our mass is not going to change. Oops, that's a plus sign. Our mass is not going to change, but our atomic number is going to have to go up to 56, because 56 plus a negative 1 is 55, and element 56 happens to be barium. A positron decay occurs when a positive electron is given off. So here you'll notice we're still thinking of this as an equal sign. 15 plus 0 was my original 15. Now, if I had, what do I add to 7 to get 8? Well, that was that positive 1. When it's a positive here, it's a positron. Notice when it's just an electron, like up here, it's a negative 1. Neutron decay is just when you're given a neutron. The nucleus emits a neutron. The neutron can also be absorbed or it can be released, depending on what side of the arrow it's placed on. If we were absorbing a neutron, it would be on the left of the arrow. So here, once again, the arrow is a big equal sign. 12 plus 1 gave me my original 13, 4 and 4. So we had to have a 0 there. We had another one that had a neutron decay. Let's pick, let's just, for example, let's say that beryllium underwent another neutron decay. So we had 12 over 4 Be. If it underwent a neutron decay, I wrote that wrong. Let me get my arrow in here. There we go. If it underwent a neutron decay, and notice it doesn't matter. You don't have to put the daughter first and the ejected particle second. I can put the ejected particle first and the daughter second. That's just how I tend to write it. So this is going to have a mass of 13. Oop, mass of 11, 12, It's an 11. And there's our 4. And we're still at beryllium, but now we have a mass of 11. Gamma decay is a change in energy only. Gamma is given off as a photon of energy. In this case, the daughter's going to be as strange as the parent. It's only a little calmer and less energetic. So let's try some of these together. So we're going to do samarium 151. So to start this, we're going to put the mass 151. Samarium is element Sm, and its atomic number is, on the periodic table, 62. It's going to alpha decay. So we've got a 4 over 2 He. 151, what do I add to 4 to get 151? 147. And my bottom number, what do I add to 2 to get 6260? And now we can go find the identity of the daughter by looking up element number 60 on the periodic table. And that is Nd, neodymium. Okay, cesium 133. 133, cesium. Cesium is element 55. It decays by beta emission. So we're going to put our beta particle. That's a 0 over negative 1 E, or beta. So my mass is going to stay the same. The 0 plus 133 gives me my original 133. My mass is going to have to go up because 56 plus a negative 1 gives me my 55. And element 56, we already saw, was barium. Uranium 234. We're going to put uranium, it's element number 92, undergoes electron capture. So now the capture is taking in an electron. There's 0 over negative 1 E. Our daughter is going to have the same mass, 234. But now look at our atomic number. 92 plus a negative 1 is going to be 91. And element 91 is protactinium, Pa. Carbon 14 changes into nitrogen 14. And we need to figure out the particle. Well, the mass doesn't change, so that's a 14. But what do I add to 7 to get 6? Well, I've got to take away 1. Oops. So minus 1 E. Okay, had a little problem on that last one. I was writing things too fast. Now it's your turn. Go ahead, pause the video, and try a few of these to see how you do. Okay, hopefully you're back. Let's look at this, cobalt 60. 60 cobalt. Cobalt is atomic number 27. It's going to decay into nickel 60. Now, nickel has an atomic number of 28. So we need to figure out the particle that's here. Well, it's going to have 0 mass. There's only 2 things that have 0 mass, a beta or a beta positive. It's going to be a negative 1 because 28 and negative 1 gives me my 27. So that's just a standard beta particle. Beryllium 7. Beryllium is element number 4. It undergoes electron capture. So our mass is not going to change. So a proton is going to be converted into a neutron. We're going to go down 1 in atomic number, and we get it's not a 0. Did you catch me there? I said it wasn't going to change, and then I wrote a 0. I always do that. Okay, there we go. So 7 plus 0 equals 7. Always double check. 4 plus a negative 1 is 3. Element number 3 is lithium. Okay, boron 8. Boron is element number 5. A positron emission. Emission means it's being given off. It is a decay. Let's just test this for a second. If there's only one thing on the left in the arrow, it's a decay. If we're adding something on the left, it's a transmutation. Okay, so we're having a positron emission. That's 0 over plus 1 E. My mass is not going to change, so that's going to be an 8. This is going to be a 4 because 4 and 1 is 5. And element number 4 is my beryllium again. Platinum 192. I need to look up the atomic number of platinum. It's 78. It is being converted into osmium 188. Osmium is atomic number 76. You have to figure out the particle. Well, it's got a mass of 4, an atomic number of 2. That tells me that is my helium nucleus or an alpha particle. I hope you did good on these. Remember, it's really easy to mess up on your numbers. I messed up on that one on purpose. You got to kind of talk yourself through and go back and do a check. 188 plus 4 is 192. 2 plus 76, 78. Just make sure you got it right. I hope this helped you out a little bit with nuclear equations. As always, stay curious, be kind, be safe. Have a wonderful day and a good tomorrow.